Welcome to Chapter 3, which is called Determinants. This is a very brief chapter, and we will only be covering the first two sections of this chapter. The first section, section 3.1, is called Introduction to Determinants. We've already talked about the determinant of a 2x2 matrix, and you may recall that the determinant of a matrix is found by finding the product of these and subtracting the product of these. But now we are going to get into finding the determinant of larger square matrices, and we are going to define them recursively, which means we're going to come up with a rule or a procedure that can be applied repeatedly. So the first thing we are going to talk about is remembering what this notation means. So this just means matrix A, and remember that this is the row and the column of a specific entry. So what we'll do is we will remove a specific row and column. For example, this here means that I'm going to remove the second row and the third column. So if I completely omit these, then I am left with this 3x3 matrix. So we're going to use this process to find determinants. So here is basically the definition of a determinant of an n by n matrix. And basically what this is saying is when n is 3, for example. So if you have a 3x3 matrix, well, then the determinant A is defined by using determinants of a 2x2 submatrix. If n is 4, so if I have a 4x4 matrix, well, then the determinant is defined by using determinants of 3x3 submatrices. And that's all this definition is saying, and it's a pretty wordy, complicated definition, but you don't have to remember it. We'll just develop some techniques that will help you along the way. So let's jump into some examples. In this example, we are asked to compute the determinant of this matrix here. So using that definition that we saw on the previous slide, here is what we will do. So that definition for a 3x3 matrix would be the following. So the determinant of matrix A is this here. Oops, minus. Okay, so this is just plugging in to that formula. So let's talk about what this means. So basically what this means is we want to identify this position, which is 2, and then we want to omit this row and this column to get the new matrix. So this piece here will be 2 times, and these go away. So the remaining matrix is this 2x2 matrix here. So this will be -1, 4, I'm sorry, this is the determinant of this matrix here. Okay, and we're going to do the same thing for the next piece. So for the next piece, we want to identify this specific entry, so row 1, column 2, which is this. So this will be minus 3 times the determinant of this new matrix, where we will omit this. So we're going to omit row 1, column 2. So this creates the new matrix. And I'm sorry if this gets messy. I just know that when I erase things, you won't really see it. Okay, then I want the entry in row 1, column 3, which is 4, times the determinant of the matrix that results when I omit row 1, column 3. So that's this matrix here. And that's all that wordy definition was saying on the previous slide. Now, there is some other notation that we can use. So it's the same thing that I have written here, but a little different notation. So instead of writing all of this, if I just use vertical bars, this represents the determinant of that 2 by 2 matrix. So it's just a little bit of shorthand notation, and mathematicians are lazy, so shorthand notation is always nice. Okay, so now we can go ahead and solve this. So I'm going to take 2 times the determinant of this. So this gives me a negative 2 minus 8, which is a negative 10, minus 3 times the determinant of this, which is 6 minus 12, so a negative 6, plus 4 times the determinant of this. This gives me 12 minus a negative 6, which is 18. Now, side note, this sign is a negative because of the formula. So just pay attention that we'll talk more about that here in a little bit, why it's negative, but just pay attention to that. So then plug this all in your calculator if needed. You get a negative 20 plus 18 plus 72 gives us a determinant of 70. Go ahead and pause this and see if you can come up with the determinant of this matrix. Okay, so if I want to find the determinant of matrix A, remember the formula is the following. And I think it's helpful to write down this formula just so you can kind of get the hang of it. And this is for 3 by 3 matrices. Okay, and I'm going to just jump in and use the shorthand notation right away. So this entry corresponds to 1 times the determinant, and I'm going to eliminate row 1, column 1. So the determinant of 4, negative 2, negative 1, 0, minus this entry is 5. So I want to omit row 1, column 2. So I'm left with this matrix. And then finally, entry A13, which is 0, times the remaining matrix when you omit row 1, column 3, is this matrix here. Now, I don't have to do anything with this final matrix because anything times 0 is 0, so that's nice. So 1 times anything, well here, this gives me 0 minus 2, so 1 times a negative 2, minus 5 times, well this is 0 minus 0, which is 0, and we already established that that was 0. So those cancel out, and I am left with a determinant of negative 2. Not so bad. you will find that we will discuss many different ways in which we can find determinants of 3x3 matrices. And in the homework, the last couple problems, I believe, there's a shortcut for finding 3x3 matrices. So, of course, you can use the definition that I just showed you 2 examples of, or you can use a shortcut. Now, this is a little messy looking, but basically here is what's happening. So this here is the original matrix. And what you'll do is you will just take this first column and rewrite it here. And you'll take the second column and rewrite it here. And then you'll take the diagonals from left to right, you take the product and you add them. And then the diagonals from lower left to right, you find the products of those and you subtract them. So just an example, if I have this matrix here. Then what I'll do is I will write this column again and write this column again. And then I'll take the product of the diagonals. So 1 times 5 times 9 plus this product, 2 times 6 times 7, plus this product, 3 times 4 times 8. And I will subtract the opposite diagonals. So the product of 7, 5, and 3 minus 8 and 6 and 1 minus the product of 9 and 4 and 2. Okay, I have no idea what that is. I made that up on the fly. So a shortcut. All right, so now we're going to dig a little bit deeper into that definition of a determinant. And we are going to address something called the IJ cofactor. So this is helpful when we have matrices that are bigger than 3x3. So a little bit of notation. So the determinant of A can be represented in this manner here, which I spoke of briefly. But this definition helps us with the next theorem. So the IJ cofactor is found by using this formula, essentially. So this here is the piece that defines the sign change, basically, from what I showed you before. And then it's the determinant of A in the row and column. So this leads to what's called the cofactor expansion across a row or a column of matrix A. Okay, and again, you know, it looks more complicated than what it is. So there's a way to remember the sign of the cofactor, which is like everything alternates. So if you look at this matrix here, when we use that IJ cofactor, the rows and the columns will alternate sign. And again, the factor, that first factor from that definition that we just saw, this determines this alternating sign pattern. So all of this leads to theorem 1. And theorem 1 basically talks about a cofactor expansion where we focus our attention on a specific row or a specific column of a matrix. And depending on whether or not we're focusing on a row or a column will depend on this. But it's ultimately the same process, but it's called the cofactor expansion. And I think that it's a lot easier to understand when looking at some examples. So I'm basically going to show you a bunch of examples of this. Let's start with this example here. It says use a cofactor expansion across the first row. This is important information to compute the determinant of A, where matrix A is given to us. Okay, so if I want to use a cofactor expansion across the first row, that means I is 1. So remember the IJ cofactor is represented in this way. Okay, and that's the definition from before. Okay, well, here is how we will go about solving this. Well, the determinant of A, we know from the previous examples and the previous definition of a determinant is found by this formula. But since we are interested in the first row, that means I has to be 1. So notice how all of these are 1. Okay, well, this piece is the new piece. So this is where the sign comes from. So basically, it's the same type of thing that we were talking about before, but we're going to focus our attention on this first row. Okay, so when we do this using this cofactor, IJ cofactor, I end up with the following. I and j in this case are 1, so I have 1 plus 1 times the determinant of this. Okay, so the first entry in row 1, column 1 is 0 times the determinant when this row and column is omitted. So it's this. Okay, then we move on. It's the same thing that we did before. Okay, so now I am in the first row, second column. So the sign is determined by this. This entry is 4 times the matrix. Once those rows and columns are eliminated, we have 5, 2, 0, and 1. And then -1 to the 1 plus 3 power. So that's the first row, third column. That entry is a 1. And that new matrix is 5, -3, 2, and 3. All right, well, it's nice when that entry is a 0. So our first entry was a 0. Anything times 0 is 0, so that cancels out. And this will lead us to an important observation that we'll discuss here shortly. Now this here, -1 to a power of 3, this results in a negative. So this is a -4 times this determinant, whatever that may be, plus this results in a +1 times the determinant of this matrix, whatever that may be. So This determinant you should find to be 5 plus 1 times the determinant of the other matrix is 21. When you add these, you get a determinant of 1. Okay, so this is an example using the first row, but we can use a cofactor expansion across any row and any column. And when we do that, this definition, this work, changes slightly. So let's look at another example. So we have a new 3 by 3 matrix, and we're going to start little here, starting with 3 by 3s. But now we are interested in the third row. So that means I is 3. So we are interested in focusing on this row here. And there's a specific reason why this third row was chosen. We could have also used the third column. In fact, we could have used any row in any column, but notice how many zeros are involved here. Okay, so let's set up our formula. The determinant of matrix A, since we are interested in the third row, first we'll look at the third row first column. Then we'll look at the third row second column. And then we'll look at the third row third column. So when we do this, we have -1 to the 3 plus 1. That's the third row first column. That entry is a 0. So if I omit the third row first column, I'm left with the following matrix. Okay, let's move on to the third row second column. Third row second column, that entry is -2. And that matrix is the following. All right, and then the last entry, third row third column, that is also a 0. So we'll have 0 times the determinant of this matrix here. Well, remember, 0 times anything is 0. So I don't even need to do anything with those terms, and I can just focus my attention on this. -1 to the 5th power is a -1 times -2 times the determinant of this. So a -1 minus 0 is -1. This results in a determinant of -2. So the determinant of the 3 by 3 matrix A is -2. And once again, you can use the cofactor expansion for any row, any column, as long as it is an n by n square matrix. So let's take a look at a larger matrix. Here, we want to compute the determinant of this matrix by cofactor expansion. So we see that this is a 4 by 4 matrix. So since this is a 4 by 4 matrix, we are going to use 3 by 3 submatrices. And this involves a little bit of work, but it's just a process that just continues. So it is our choice if we want to use a row or a column, and which row and column we want to use. So you want to look for a row or a column with a lot of zeros. And if I'm looking at this, I will notice that this row here, row 2, so I is 2, I notice that that row has a lot of zeros. So that's what I'm going to focus on. So when I set up my work, the determinant of this 4x4 matrix A, I'm going to focus on the second row first column, plus the second row second column, plus the second row third column, plus the second row fourth column in this case, since it is a 4x4 matrix. Okay, so now when we cancel out a row and a column, my submatrix is going to be a 3x3. All right, so when I set this up, second row first column, that entry is a 0, and my submatrix ends up being the following. So it's the same thing we had before, but now we have a 3x3. So that's this here. Okay, let's look at this one. So we have -1 to the 2 plus 2 times. So I want the second row, second column, which is 0 times. So now this cancels out, and I'm left with this. Now, normally in my work, I would erase things to clean it up a little bit. But I don't want to do that in this case because I don't want you to miss what I'm writing. Okay, so now we're just following this pattern. So now I want the second row, third column. That is entry 3. And if I cancel this out, then I'm left with the following in the first row, and then the second row, and the third row. And I think you have an idea. But now when I go to my last entry, this is also a 0. And remember, anything times 0 is 0. So I'm not even going to bother writing that down. And you may see that this is 0 and this is 0. So this is really the only piece we're focusing on. Okay, well, this is a -1 times 3 times the determinant of this. So what we're going to do, since this is a 3x3 matrix, we get to do it again. So I'm going to write this on the next slide so that I have a little more room. Okay, so we had that -3, and we want to find the determinant of this matrix. All right, so we get to choose which column in which row, or which row we want to do our cofactor expansion on. So when you are deciding, look for zeros. And I see that this entry here is a 0. So I can either use the second column or the third row. It doesn't matter. I'm going to go ahead and try a column now, and I'm going to try the second column. So that means J in this case is equal to 2. I haven't done an example with a column yet, so I thought I'd give it a try. Okay, so if I want to find the determinant of this, I'm going to have -3 times. Now let's break this down. I want the first row, second column. Oops. First row, second column, plus second row, second column, plus third row, second column. So notice that I'm always dealing with column 2 because that is the one I started with. Okay, so moving along, for this first piece, I want the first row, second column. So this is my focus column. So first row, second column, I have -1 to the 1 plus 2 times. That entry is -2 times. My new matrix is 2, 2, 5, 5. Okay. Plus -1 to the 2 plus 2. All right, so my second row, second column, that entry is a -4 times that determinant is, or that matrix, that 2 by 2 matrix is this one, plus, now, sorry, my dog sees a squirrel. Hang on. Okay, third row, second column. Third row, second column, that entry is 0. Anything times 0 is 0. Okay. All right, so now let's continue to simplify this. This is a -1, so a -1 times 2 is 2, times the determinant of this is 10 minus 10, which is 0. This is a 1 times a -4. So -4 times the determinant of this is 5 minus 4, which is 1. So this goes away. So I have -3 times -4, which is a positive 12. And there you have it. So that's finding the determinant of a 4 by 4 matrix using cofactor expansions. So there's another theorem in this section, theorem 2, which is written here. And it looks a lot fancier than what it really is. And basically what this is saying is if matrix A is a triangular matrix. So remember, a triangular matrix means we have zeros down here. So anything else up here. Okay, so if matrix A is a triangular matrix, then the determinant of that matrix is the product of the entries on the main diagonal. So you would find these entries, and so there would be 3 in a 3 by 3 matrix, there would be 4 in a 4 by 4 matrix, and you would just find the product of those entries. Okay, and that is the determinant. So it's helpful to put these matrices in echelon form. Another thing, if there are all zeros in a row or a column, if there are all zeros in either a row or in a column, then the determinant is equal to 0. Some people want to know what exactly a determinant represents, and you can dig deeper into this if you'd like, but ultimately the determinant represents the area of a specific parallelogram depending on the size of the matrix. So this kind of explains it for you. But this wraps up the material for this section. Enjoy.